the line rotates clockwise about the pivot P until the first time that the line meets some other point Q. It's Q, so the line's rotated around until it meets Q. This point takes Q as the new pivot, and the line now rotates clockwise about Q until it meets the point of S, and the process continues indefinitely. So it's going around there, it's rotating to Q, and then it's going around there, and it's going around there, etc. Show that we can choose a point P and S and a line going through P such that the resulting windmill uses each point of S as a pivot infinitely many times. So let's say, supposing you choose the line right and the point right, then it will be an infinite process. Why is it called a windmill problem? Well, because it kind of looks like a windmill. It was only after thinking about this for a little while that I discovered that this Math Olympiad problem had been devised for the International Mathematical Olympiad that took place in the Netherlands by one Jeff Smith.
No, Dan Schwartz. Oh, Jeff Smith devised it. Okay.
Jeff Smith devised it. So he said. So there's the problem, and the idea is to solve it by discussion according to these rules of engagement. All are welcome, no spoilers, not a race. Update wiki, meta comments go in the discussion thread. Be polite and constructive and make your comments as easy to understand as possible. So that's an invitation to collaborate. And what happened with this problem? Well, people duly collaborated. There were about 150 comments in 47 minutes. No, 74 minutes. 74 minutes. This, of course, depending on what time zone people are in. You know, some people didn't get a chance to play unless they have to be up at 2 a.m. And then the problem was duly solved. Well, Alison has a whole talk about this in a rather long paper, but I'll just summarise. One of the things we were doing was just looking at the nature of the comments. After all, this is I showed you a flavour just now. Just go back to it there. Yes. So you see the kinds of comments. So this is, we've kind of dived in the middle bit, but so Galler said something or other at this point where the pivot changes, we do something or other. And then Garth says, yeah, now, well, what if we do it this? Maybe that's a simplification. And then Galler's tossed in another idea, and so on.
Say 74 comments. How many different contributors?
150 comments. How many contributors are there?
Yeah, I think it was, there were a lot of this, I think that's around 50.
Yeah. So it was a bit like this. Some people did a lot of work, some people just threw in one or two. And some people, what's quite interesting is and this is even more striking with much bigger problems, is of course different people bring different skills to the party. And so part of the sort of social thing that's going on is you actually want to sort of keep people in the conversation because they might not have much to contribute here, but they might know something else useful further down the page. There's actually a reason for being polite and not burning people off. And you can see the kinds of discussion you can see the tone of the kind of discussion that's going on. So here, for instance, Jersey has come up with an example. What happens here? I must be missing something here. And Joe says, yeah, you are. You've got something wrong, and so on. So it's very much like the sort of discussion you would have in the pub. You're throwing around ideas, they may or may not be right, so on. And so when we analysed it, one of the things we were looking for was, well, what sort of things are happening in the conversation? Well, a lot of the things are conjecture, what happens if kind of things. About 10% of them are playing with the with concepts of different kinds. And one of the basic concepts is actually, you see, You start off with a line going through a point. And so I drew a point and I drew a line going through it like that. And of course, but a number of people first playing with the problem actually don't draw it like that. They draw a half line. And if you draw a half line, it's a different problem. The answer isn't actually true. The problem is actually true. So some of it's playing around with that. Only 14% of this is actual final proof steps. You know, the kind of thing that would, if you were to write this up a la Principia Mathematica, only 14% of all that stuff would actually be in there at all, because all the rest of it is examples and conversation and so on. 33% is examples, so what happens in this case, what happens in that case. 33% is other. Well, a lot of other is, you might think of it as just sort of miscellaneous chit-chat, but it is sort of social news, you know, nice idea, keep them coming, you know, that kind of thing. You know, they don't spend a lot of time on chit-chat, they power through to get to the answer. But, a lot of it is a surprising amount of stuff. Since this is the year of Turing, Alison and I amused ourselves by thinking about, well, we were thinking about, can computers do this stuff? What do you think of, what do you make Polymath, taking part in Polymath, your Turing test? You see, your Turing test is supposed to be, can a person pass as a machine? I'm sorry, can a machine pass as a person? Not the other way around. Can a machine pass as a person? Well, what if your test, what if you were having a rather restricted kind of person? Could a machine take part in this polymath discussion and pass as a person? Well, and if you look at what machines are capable of, which would be a whole other graduate course really, machines can do some of the things that are appearing in this discussion, like coming up with examples, thinking about concepts, automated proofs. But they totally lack many of the other things, and many of the other things that we're seeing in this, like dealing with analogies and diagrams, dealing with misunderstanding and error, developing and comparing alternatives, fleshing out a rough argument, and so on. So there's an awful lot going on in here, which is mathematical practice, is making things happen, but is not captured by our current understanding of machine thinking. Alison knows a lot about Lakatos, and certainly knows a lot more about Lakatos than I do. But one of the interesting things we were doing in looking at this was looking, you can sort of ask yourself the question, was Lakatos right? Lakatos, you may remember, produced a rational reconstruction, as you call it, of a compensation of a mathematical proof, including all the conversation that goes on as the proof happens. And it's and of course you can go through these discussions and look for Lakatos moves, if you like, look for the phenomena that Lakatos reports about, the kinds of use of examples and so on that Lakatos reports. And you find a lot of that. You also find Lakatos like things that, as far as we know, Lakatos didn't write about. Well, the other thing we were looking at was math overflow. Lakatos provides you with one conversation, if you like. Polymath provides you with about, I think they've had about 10 or 12 polymaths so far, 10 or 12 conversations. Math overflow provides you with 27,000 mathematical conversations. And we're looking at math overflow again, just to see what happens in these conversations. And what we decided to do in looking at math overflow was restrict to questions on group theory, but rather, so just to say what math overflow is. Those of you who remember the old sci.math.whatever news groups, it's one of those. It's a site that you go to and ask mathematical questions, but it has a number of rather a number of features that make it more pleasant to use. Not just the fact it looks prettier, but things to do with rating questions, tagging questions, rating questioners, and so on. Here's a typical question. Don't worry if you don't understand the question, because you can sort of parse it. Which finite non-abelian groups have long chains of subgroups? Well, asking for examples of something or other. So here's the question asked by William DeMeo, edited by Frank Ladish. PM, whoever PM might be, has said, have you considered such and such? The person who answers the question says, oh no, I haven't looked at those. I'll go back and have a look at those. And then somebody has produced a more detailed answer, somebody called Derek Holt, who people in the UK pure maths community will know. This is Facebook for mathematicians. Keeps them off the street. And Derek Holt, people who know Derek Holt know he's one of these wonderful people who knows an awful lot about an awful lot. And sure enough, he knows the answer to this. And he's come up with something or other. And Jack Schmidt says, hey, thanks, that's really neat. So Jack Schmidt actually isn't the person who asked the question originally. Jack Schmidt is somebody else who's just getting rather interested in this. And Jack has said, well, you made a mistake here. Why does Q have to be odd? And Derek said, oh yeah, I guess I have. But, you know, I chose this example because you see they're being fairly relaxed about, this is somebody just typing an idea rather fast. They're being fairly relaxed about mistakes and correcting each other's mistakes and so on. And then William DeMeo will say, wow, that's pretty cool. Thank you, that's it. And you'll see the ratings in action. The questions are rated, the answers are rated. There are there's a whole lot of the individuals are rated. So Derek Holt likes asking questions. It's got a hugely high rating. You can get badges for being helpful in different ways. All sorts of things you can do. I thought it would be quite interesting to go away and look at this and see what we could learn from this about mathematical practice. And I cut down the 27,000 questions to 1,377 questions on group theory. Why group theory? Because that's what I did my PhD in, and they're the only questions I actually have a hope of understanding. Looking particularly at what kinds of questions people are asking and what sort of phenomena occur in the answers. Remember, we're trying to think about how can we get computers a bit better at doing mathematics. And because I'm on sabbatical with in Edinburgh, where there is, as was referred to this morning, a rather fine group of sociologists of science, they don't really talk about the science wars anymore, as you said. They're all off looking at synthetic biology, large-scale software infrastructures. I'm trying to be a bit principled and use methods of qualitative analysis, but methods of qualitative analysis also have their own wars if you're a sociologist. But the nice thing about talking to some of the Edinburgh sociologists was they told us how to avoid the wars. Just walk this way all the time. Of course, we're looking at lots of text on a computer, so we could throw all sorts of computery stuff at it, but we haven't yet. So, the idea is to look at the questions and try and come up with a classification of what kinds of questions are being asked. And I had quite a few goes at this, but eventually we sort of fell into looking at we fell into a classification that seemed to work. And these are some of the categories we were using. What's going on? There's quite a lot where somebody just describes a mathematical phenomenon and says, well, I've seen this. I think somebody must have seen this before. What is it? People asking for references. People asking for examples, people straight out asking if something's true, people seeing, and so on. And in fact, when you do the classification, the majority of questions are indeed people saying, is such and such true? About a quarter of them are, what is this? They classify different proof. Different proof is one that quite often turns up in group theory. There's been one massive theorem in group theory, or finite group theory, over the past 30 years, which is the classification of a hugely complicated theorem which classifies finite simple groups, classifies all groups of a particular kind. And so you very often get questions along the lines of, well, is there a proof of such and such a result that doesn't require me to use this great big sledgehammer called the classification of finite simple groups? And that's where, those are the kinds of questions where you quite often get answers of the kind that would never be captured in a maths research paper, because there's somebody saying, no, that approach wouldn't work because, or so-and-so tried that, but it didn't work because, you know, you're capturing a lot of knowledge in this thing that would otherwise be sort of. So those are the kinds of questions people were asking. We then started looking at what kinds of things occurred in the answers. We looked at, well, was the question resolved or moved on? And it turned out that in the majority of cases, you know, people ask this question out there, and somebody somewhere has something to say, which doesn't necessarily answer it completely, but adds some of human knowledge on the thing. What kinds of things occur in the answers? Well, very often people are pointing other people at references. And you might say, well, why didn't you just use Google then? Well, the answer is these questions aren't really questions like, you know, what is the capital of Poland? They're not really questions that you can use Google on. But they are questions where, you know, I'm the world expert in left-handed widgets, and I've got this question, and it turns out that the one person who can answer it is a person who knows about right-handed widgets, but I hadn't realised that. This mechanism is not going to be quite that close. And then there are a number of other things that occur that look out of the text going for. So, what did we learn so far? Well, we learned that it's very efficient at what it does. Most of the questions are resolved or moved forward, and even if they're not, they still provide information. Why does it work so well? Well, it's capturing expertise that isn't really in mathematical papers. You know, your typical mathematical paper starts off with, well, if you're lucky, it's a sort of paragraph of chat, if you're lucky. Then there's the statement of the theorem. Then there's the proof of the theorem. Then there might be a little bit of discussion at the end. But this will be in natural language or in mathematicians' use of natural language. But it won't typically. The style of the presentation of mathematical papers doesn't capture all the byways. It doesn't capture the, I got completely stuck on this, so I did that, or, and here's this useful example I found along the way. There are a great many other things that the practicing mathematician knows about the problem they were trying to solve that they don't write in the paper. And this captures the stuff that isn't written in the papers. This also finds the expert, and all those mechanisms to do with tags and ratings and so on. You may have seen those sorts of things before. You've seen them on Amazon, you've seen them on eBay. You know, all those technologies invented for other things are actually being used here to just to help this site be a bit more easy to use, but sort of but help you find the expert. And well, I suppose this is a bit of a virtuous circle thing, really. You do get participation by the expert. So You know, this is an opportunity. If you have a sensible question, people will engage. And I don't think it's actually quite a remarkable tribute to the mathematics research community that you could be somebody completely unknown from a non-Western country, and if you asked your question in sort of reasonable English and you understood the conventions of the game enough, you could get an answer from a top mathematician, you know, who will treat you with respect. And it is a very civilized and polite community. One can contrast, I don't know if anyone's ever looked at the Foundations of Mathematics email list. Yes. Well, for those who haven't, the words very civilized do not immediately apply to the Foundations of Mathematics email list. It's quite a sharp tone, rather often, you know. An unknown mathematician from an unknown part of the world would be taking their life in their hands if they took part in a discussion of quant. They wouldn't on here. And when people do ask questions that are a bit naive, then they you know, sometimes people ask questions that are well-intentioned, but to which the answer is basically, it would be a good idea if you went and read a first-year textbook before you try to think about this, and they will get that answer, but politely. But all of this, so it is, I think the mathematics community should actually be quite proud of itself for that sort of, for this aspect of it. I was talking to somebody in chemistry who said, well, she just couldn't imagine something like this happening in chemistry because it's just a lot more competitive, it's a lot more cut and thrust. You wouldn't reveal your questions. You wouldn't sort of give away your knowledge in this way in chemistry. I don't know if that's true, that's just what I'm told by chemistry. So there are all of these things, and all of these things are things that people studying these other, way off things like e-science or internet science or sociology of the internet or something, go and think about it. One can see all these things in this. And then again, when we look at what's occurring in the answers, lots of examples, lots of references or history, quite a bit of clarification of definitions or concepts. And those questions, sort of those kind of what's going on type questions, they are the questions that sometimes you'll ask when you're trying to learn something. You'll read a definition of something, and then you'll think of an example, and you'll say, but how does that definition fit this example? Sometimes these things are actually clarifying Wikipedia entries. And the nature of the answer is then sometimes actually Wikipedia is wrong. People don't have big, long, complicated proofs. They used to have lots of Lakatos type moves, lots of chat.
What is a Lakatos type move?
Where can I start? So, Lakatosh's book, Proofs and Refutations, he discussed, it's a term I'm using for things like the different notions of the different uses, notions of how you use counterexamples that Lakatosh had. Okay, so it's just a blanket term I'm using for the kinds of things that Lakatosh observed.
They're different.
Yes, I know. Yeah, that's what I mean. Sorry, there could be a whole, you could write a whole very lengthy paper on the different, there are different, yes, I know, there are different ones. There are different ways of using counterexamples, and I think we spotted all of them. But then we spotted other things that are of that nature, but as far as we know, Lakatosh didn't write down. So, that's another it's a good question. So, lots more to think about. Lots more to think about what computers might do. And from the point of view of this conference, lots more to pick up on from the perspective of mathematical culture. So you can look at all of this, and one of the questions that Robin Williams, who's a sociologist in Edinburgh, got me thinking about, I was saying, well, wow, isn't this a new and exciting culture? And he said, well, no, actually, maybe the reason that this is working so well is that all mathematicians are doing is they're taking something that works well in the real world, conversations in the coffee room. They know how to do that. They know how to do conversations in the coffee room as an informal mathematical practice, and they've just translated it to the web. And then they sort of picked up on various webby mechanisms like ratings to do it well. They know how to do constructive, friendly conversations in the coffee room. They also know how to do good old arguments in the coffee room. And so the good old arguments they put on FOM, and constructive, friendly conversations they put on here. Is it a new mathematical culture or a different, a manifestation of an older mathematical culture? But the fact that it's there allows us to study it in detail and allows us to allows us to gives us an evidence base for looking at a great many more questions about it. Okay, thank you.